In this video, we will learn what a buffer is and how to make a buffer. Buffers are solutions that resist the change in pH when small amounts of acid or base are added. Buffers are made together by mixing together a weak acid and its conjugate base. So let's take an example. Previously, we had mentioned acetic acid. Acetic acid is formed from our acetate ion, and when that reacts with water, then the conjugate base for that is C2H3O2 minus, and we would get the H3O plus ion. This reaction, since it's made with a weak acid, it's also reversible. And so this reaction goes both ways. I'm going to rewrite my arrows. So this reaction goes both ways. And so when we talk about mixing together a weak acid and its conjugate base, then what we're really saying is that we need to increase the concentration of the conjugate base by quite a lot, because normally a weak acid in solution has a very small amount of this, and it's mostly the intact weak acid, which is a small amount of this conjugate base. But if we add a large quantity of a conjugate base in the form of an ionic salt, then we can increase that concentration of the acetate ion by quite a lot. And then we can have almost equal amounts of my weak acid and my conjugate base. So I'm adding extra of an ionic salt to increase the molarity of this conjugate base. It doesn't matter what the cation is here. That doesn't matter. What matters is that I have the anion of the conjugate base. The sodium would just be a spectator ion. So let's look at how the solution resists change in pH. So if we had neutral water, which is not a buffer, and added H3O+, then it would drastically change the pH and make it very acidic. If we added OH- ions, then it would make our pH very basic. But on the other hand, if we had a buffer solution with the same pH as our water, pH 7, and then we added H3O+, that's going to add more here, and that's going to make our backwards reaction react more, and we're going to reform some of that. And as a result, we have a very small decrease in our pH. On the other hand, if we add OH- ions, that's going to neutralize our hydronium ion concentration, and we will have a very slight increase in our pH. So our buffers work by neutralizing both our acid and our added base. So here's a diagram to show you that if I add H3O+, then that's going to bond with my conjugate base in order to reform the intact molecule. If, on the other hand, I add my OH- ions, that's going to react with the acid to make water, and then I'm going to be left with my conjugate base. And so this solution can react with either acid or react with base. It can do both. And so since it can react with both, it can resist change in pH. Your body uses a buffer system in order to maintain a constant pH. The pH of your blood is 7.4. on average. But there is a range. It can range from anywhere between 7.35 to 7.45. And so at the center of your body's blood buffer system is this hydrogen carbonate ion. And so we have learned about this hydrogen carbonate ion before. In chapter 10, we learned that this hydrogen carbonate ion is unstable and it decomposes into carbon dioxide gas and water. And so you breathe out carbon dioxide. And that's one way that your body can help maintain its buffer system. This hydrogen carbonate can also react with water in order to make H3O plus and the hydrogen carbonate anion in an acid-base neutralization type reaction. So you can go either direction. You can form this or you can form this. And that's how your body maintains its constant pH. If your blood pH gets too low in pH and you're too heavily on this side of all the equations, then you are in acidosis and then you die. If you're more this way, then you're in alkalosis, which is too basic, and then you die. Let's practice identifying buffer systems. I want you to look at each pair and decide which combinations would produce a buffer solution. Go ahead and pause the video and try to decide which ones will make a buffer solution. All right, let's go over this. So remember, we're looking for a weak acid plus the salt of the conjugate base. So this is HCl is a strong acid. So that one's not a buffer. Next up, we have our H2CO3, hydrogen carbonic acid, and that is a weak acid. And the conjugate base of it is sodium hydrogen carbonate, and so this one will form a buffer. Now we have phosphoric acid. Phosphoric acid, is that one of your strong acids? It is a weak acid, but this is not its conjugate base. That's not the right conjugate base. And lastly, we have to remember that this is a carboxylic acid. And so my conjugate base would have CH3COO. And this, all carboxylic acids are weak acids. This is the conjugate base of that. And so this one will be a buffer. All right, lastly, we'll talk about titrations. Titrations are a method of controlling how much of each solution you're adding to another solution in order to quantitatively figure out what the reaction stoichiometry is and how much you are doing. So we'll have one lab experiment where we have to do an acid-base titration, but we are analyzing a solution down here. So this is what you're analyzing. And then we have what's called a burette here, filled with a solution. And this is your analyte. That's what your titrant goes in into the burette. I can talk. And so we'll open the stopcock here and drip small amounts at a time into here. And when all of the acid and bases are stoichiometrically equal, then we're at our equivalence point. And so that means that we are nothing limiting, no limiting reactant. I'll just write no limiting reactant. No limiting reactant. No excess reactant. Everything will be perfectly on stoichiometry. So by on stoichiometry, we mean exactly what we need based on our stoichiometric coefficients. Now, we can't see when that equivalence point happens. And so we use indicators that change colors near where we expect our equivalence point. But the end point, when we stop our titration, is not necessarily equivalent to where the end point and the equivalence point are not necessarily at the same pH, but these are different indicators that we have, and we'll just make an assumption that endpoint and equivalence point mean the same thing because we're in Chem 3A. But you can see that some of these things change colors. And so phenolphthalein is the one that we'll be using in lab. And so that changes colors right around here. But we'll be saying that's close enough to pH 7 that we'll call it good. So when we are completely neutralized, we're going to be changing colors. Phenolphthalein changes from clear to light pink, and some of these other ones also have some pretty cool color changes depending on pH. The good news is about titrations is that there's no new math. Just stoichiometry. But it's the easier stoichiometry because we don't have to worry about limiting reactant.